Welcome to Learning to Engineer. What is a transient response and how does it differ for different kinds of systems? What factors affect the transient response? Is it the signal input or the inherent components of a system? We are also going to discuss in detail about the Laplace transform part and the basic Laplace transform formulae involved in it. You don't have to be a master of Laplace transform in order to study control systems. You just need to learn a few basic concepts and few formulas, of course. So let's get started. Consider this first order system. The transfer function is 1 by s plus a. When the characteristic equation of a closed loop transfer function has the highest power of s as 1, then this is a first order system. And the highest power of s in this is 1. So this is a first order system. So we are going to find out the time domain response c of t using the transfer function of this. So how to find out that? First thing is you have to first find out the response in s domain. What is c of s? Then you have to apply Laplace inverse and find c of t. That's all. Okay. So first thing is how to isolate this term alone. The c of s will be r of s multiplied by the transfer function 1 by s plus a. The r of s can be anything. It can be a step input, ramp, parabolic or impulse or anything. If it is a step input, then r of s will be in the format of a, which is a constant, divided by s. If that is a ramp input, then what will be r of s? It will be of this format, a by s square. Okay. So for a parabolic input, what is the r of s? This is going to be a factorial divided by s power a plus 1. Okay. So depending on the type of signal input, we have to apply the corresponding r of s over here. Okay. So let's say this is a step input. So the c of s is equal to a by s multiplied by 1 by s plus a. In order to find out the inverse Laplace transform, this should be in a standard format. Currently, it is a multiplication of two terms. I will label this as term number 1 and I label this as term number 2. Let's say if c of s, let us say, okay, if c of s is just a by s, which is the first term, okay, then easily we can find out c of t. What is c of t? Simple, it is a. Because in the standard results that you are seeing on the screen now, the Laplace transform for a constant term a is a by s. Okay, so inverse Laplace transform will be a. It is a direct conversion. Let us say the c of s is just 1 by s plus a. Okay. So easily we can find out the inverse Laplace transform from the basic formula. This will be e to the power minus at. But it is a combination of both of them. It is a multiplication of them. This is not equal to the inverse Laplace transform of a by s multiplied by the inverse Laplace transform of 1 by s plus a. That is not the case here because we have a multiplication sign in between. Okay. So we want it in the format like this. We want it in this format where c of s can be splitted as an addition of these two terms, a by s plus 1 by s plus a. We want it somewhere in this formula. We don't want a multiplication in between. We want an addition in between. So how we are going to make that? With the help of partial fractions. Okay. So we want it in this format where this is equal to x1 divided by s plus x2 divided by s plus a. Okay. So only when it is in this format, we can apply the inverse Laplace easily. When we have a multiplication in between, we cannot directly apply the inverse Laplace transform. That is the reason why we are going to partial fractions. What is partial fractions actually? When you have two terms which are a multiplication of each other, two fractions, this is a fraction, this is a fraction. They are the multiplication of each other, and we are trying to separate them by having a addition or a subtraction term in between, so that individually we can find out C of t by, where C of t will be the inverse Laplace transform of x1 by s plus the inverse Laplace transform of x2 divided by s plus a, where x1 and x2 are constants. So only when we are able to separate them, we can directly apply the inverse Laplace transform formula using the standard structure itself. Otherwise, it is difficult for us to apply the inverse Laplace transform, and that is why we are separating the multiplication terms into these two terms, and this is done using partial fractions. Okay, so these are the standard results of partial fractions. We are using the first case in this case. Okay, our job is to find out x1 and x2 by using partial fraction methods. Okay, so only when we do that, we can easily substitute it. So what is C of t now? C of t will be Laplace inverse of x1 by s plus Laplace inverse of x2 divided by s plus a. So we will have the first term now. What is C of t? This will be x1 plus x2 into e to the power minus at. This is C of t for a first order system. Now let us find out x1 and x2 by partial fractions. Okay, so we have a divided by s into s plus a is equal to x1 divided by s plus x2 divided by s plus a. Okay, so let us apply LCM and have it as the same term, s into s plus a in the denominator. So I am multiplying x1 by s plus a and x2 by s. I hope you guys didn't forget the basic concepts of fractions, right? You would have learnt in your middle school. Okay, so the denominator and this denominator is same, so therefore the numerator is got to be the same. So a is equal to x1 into s plus a plus x2 into s. Okay, so the s term is a common term between these two things. So let's have the s as 0 for now. Put s is equal to 0 on both sides. So you will be getting a is equal to x1 into small a, and this is 0. So what is the value of x1? Capital A divided by small a. Okay. So now we are going to put s is equal to minus a. Okay, why we are doing this? Why are we putting s is equal to 0? Why are we putting s is equal to minus a? Why can't we put s is equal to 5, 10, 15? Why can't we do that? A very basic concept of partial fractions. Okay, so you should be able to answer this question. So when we put s is equal to minus a, this term will vanish. So we are getting a is equal to minus a into x2. So what is the value of x2? x2 will be minus of capital A divided by small a. We have got x1 and x2 now. Okay. So let's substitute, and we are now getting a divided by s into s plus a is equal to a by a divided by s plus minus a by a divided by s plus a. So now what is the time domain response of C of t? This will be the Laplace inverse of this plus the Laplace inverse of this, which we did earlier. We can now substitute the value of x1 and x2 right away. A by a minus a by a e to the power minus a. So we can take the a by a term common. 1 minus e to the power minus 8t, where What is capital A? Capital A is equal to the step size of the step input. Okay. So what is small a? The small a is taken from the transfer function. Okay. Or we can say that the time constant is equal to 1 by a. What is time constant of a system? The time constant is the time at which the response reaches 63.2% of its output. Look at this table. This shows the response in time domain. V by V is the output voltage divided by input voltage. Okay. And this is the response. The red line shows the response of the system. At one time constant, the response reaches 63.2% of the final value. So in this case, I will draw a small line. Okay, the final value FV, okay, the final value is 10 in this case. What is 63.2% of 10? 6.32, right? So when does it reach 6.32? It is somewhere here. And this interval, it reaches 63, it reaches 6.32 at what time? At 1 second. So the time constant of this system tau is equal to 1 second, because at 1 second the response reaches 63.2% of the final value. Okay, so with the help of time constant we can know at what time will the system reach steady state. This is one time constant. In the second, this is the first second, this is the second second, and at second, which is 2 time constant, it reaches another fraction of the input. And at the third time constant, it reaches really close to the output, but it's not the final value. At the fourth time constant, it is almost 99% of the final value. And at 5%, it is somewhere 99.8% of the final value, which we call it as steady state. So from this, what do you understand? At one time constant, the percentage of maximum is 63.2% of the maximum. At 2 time constants, this will be 86.5 of the steady state value. At 3 time constants, it's going to be 95% of the final value. At 4 time constants, it is going to be 98.2 of the final value. It is not 99. I told you it is 99, which is 98.2. 98.2 percentage. The final value is 10 in this case. At 4 time constants, what is the value of C of t? C of t is equal to 0.982 into 10. Okay, what happens at 4 time constant? What is the response? 98.2% of the final value. Okay, so this is the meaning of a time constant. When you say that you know the time constant, you can know how quickly the system will settle and what will be the response of the time at that particular time constant. Time constant is just nothing but time. Its unit is second. Okay. So what happens in the first time constant, which is 1 second, the response will be 6.32 volt, which is 63.2% of the final value. So at second time constant, it is going to be 86.5 of the final value. Third time constant, it is going to be 95% of the final value, and at the fourth time constant, it is going to be 98.2% of the final value. Now we will understand the RC value here. Okay, time constant is equal to RC. How is that so? We are going to look at that with the help of an electrical system. We are measuring the voltage across the resistor, voltage across the capacitance, and let us denote that as V0 of S. So I am putting the multimeter across the terminals of this capacitor and measuring the output voltage. Okay, so what is the transfer function of this system? Basic definition. What is the basic definition of transfer function? The output voltage divided by the input voltage is equal to the transfer function of this system. So for this system, let us do the KVL equation. Okay, so by the help of the Kirchhoff's voltage law, I hope you didn't forget this law. Okay, so if you had forgotten, you can watch any of these videos in my playlist and understand this very well, and then you can come to this video. So what is VI of S? VI of S will be R into, okay, this current that's entering them is I of S. Since it is a series circuit, I of S is the same across this resistor as well as this capacitor. Okay, so R into I of S plus I of S divided by CS. If you do not know how I arrived at this, please watch this video. Okay, so what is the output voltage? It is the voltage that is measured across this capacitor, right? Voltage is equal to current times the impedance, right? So I of S into the impedance 1 by CS. So now let us find out the transfer function. What is the transfer function? V naught of S divided by VI of S, correct? So we will just divide and find out V naught of S divided by VI of S, which is equal to, so how can I simplify? In the denominator I can take the I of S term as common so that I can cancel with the numerator. Okay, now I can take the LCM in the denominator and have this as RC into S plus 1 divided by CS. So these terms will cancel, and what is the transfer function of this first order system? Output by input, which is equal to 1 divided by RC into S plus 1. This format of the time constant is called as time constant form. Why is this called as time constant form? Because we can find out the time constant from this term itself. Okay, so what is the time constant in this case? The time constant tau is equal to R multiplied by C. The time constant of a first order system is RC. Okay, so only depending on this the system's settling time depends, and that is the reason why we keep the transfer function in time constant form to know what is the order of a system, and directly we can find out the time constant just from the transfer function itself. Okay, so this form of transfer function is called as the time constant form of transfer function. Now we are going to look at one problem in the first order system so that you understand how the system settles and what is the impact of time constant on the system. A mercury in glass thermometer has an overall transfer function of T of S is equal to A by S plus A. If the thermometer requires 1 minute to indicate 95% of the final value for a unit step excitation, find the value of A. This is the question. Let me just jot down the given details for you. It is given that this is a mercury in glass thermometer and the transfer function of this is given as A divided by S plus A. Let this A be any constant. Okay, this is just a first order system for you to understand. Okay, the next thing is C of T1. This will be 0.95 times the steady state. Okay, it's given that if the thermometer requires 1 minute to make 95% of the final value for a unit step excitation. So it's saying that it will take 1 minute where this T1 is 1 minute. A response at 1 minute will be 95%, which is 0.95. 95 by 100, 0.95. 95 by 100 times the response at steady state. Infinity means steady state. Okay, and it's given that the excitation is unit step. So it's given that R of S is equal to 1 divided by S. We need to find out the value of A for this system. Okay, so this is really simple, right? We know the value of the transfer function C of s by R of s. R of s is also given. So what is C of s? C of s will be R of s multiplied by the transfer function A by s plus A. So which is equal to 1 by s into A by s plus A. C of t, as t tends to infinity, is going to be limit s tends to 0 s into C of s according to Laplace theorem rules. Okay, this is the final value theorem. Okay, according to the final value theorem, the value at time domain and time approaching infinity is same as in s domain, s approaching 0, s into C of s. This is the final value theorem, correct? So we can find out the steady state by this means. So what is C of infinity? C of infinity will be limit s tends to 0 s into C of s, which is this 1 by s multiplied by A by s plus A. So this is equal to 1. At infinity, the response's value is 1, which means that the value of temperature at steady state is 1. Okay, whatever be the unit, it's 1 degree Celsius or whatever, it's 1. Okay, so it's given that C at 1 minute is equal to 0.95 times the steady state, which is 1. Okay, so what is the value of the response at 1 minute? This will be 0.95 in whatever units the temperature measures. Okay, just note this point. Okay, we will dig into the transfer function. What is the transfer function? A divided by A plus S system. We have to convert that into time constant form. So for that, we will divide the transfer function by A on both sides, so that we will get a 1 factor over here. So it will be 1 divided by 1 plus 1 by A into S. The transfer function in time constant form will be this. So what is the value of the time constant? Time constant is equal to 1 divided by A. Let us note down this as well, and we know that the response at 1 minute is 0.95. 95 percentage of the final value, which means that this occurs at 3 times the time constant. Okay, which means it is 95% of the final value. So 95% of the final value will occur at 3 time constants. Okay, so this means that 3 times tau is equal to 60 seconds, and what is tau? 60 divided by 3, which is 20 seconds. At 20 seconds, the system's response is going to be 63.2%. So the C of tau time constant will be 63.4 by 100 times the steady state value. So with this, we understood that the time constant is equal to 1 by A, which is equal to 20 seconds. So what is the value of A? A is equal to 1 divided by 20, which is 0.05. A is equal to 1 by 20, which is 0.05. So in this video, we understood how to derive the time domain response of a first order system, and then we also solved a problem. We understood one thing, that the transient response depends on the system components and not on the system's input. Thanks for watching. In my next video, I will be explaining about the second order systems. Thank you.